Okay, this is a lesson on Taylor polynomials, which are extremely interesting and part of the syllabus for Math 176. You want to approximate a function by a polynomial. The best approximation is the Taylor polynomial, and there is a simple command in Maple to compute the Taylor polynomial. It's simply Taylor with a lowercase t, and put in the function you're interested in, for example, e to the x, exp of x. And the Taylor polynomial is computed around some central value. If it's x equals 0, it's called a Maclaurin polynomial. X equals 0, for example. And if you want, let's say, the first 4 terms of the Taylor polynomial, you have to put in the number 5, 1 greater, because you'll get an error term as well. So this is it. This is like this miraculous formula. E to the x, when you look at its Taylor polynomial of degree 4, it's this 4th degree polynomial, and this is the error term. So order x to the 5th. Now, if you want to see how nicely this approximates e to the x, let's say we plot exp of x. That's the exponential function. Maybe because it goes up so fast, x going from 0 to 100. Maybe that's a little bit better. Oops. Sorry, not x goes from 0 to 100. X goes from 0, from minus 10 to 10, let's say. And y goes from 0 to 100. Because we know the exponential function is never negative. That's what it looks like. Suppose we take this 4th degree polynomial and plot it together with the exponential function. So we're plotting 2 curves, e to the x, and this 4th degree polynomial. What does it look like? Wow. So in this area, the blue and the red, actually, they coincide really well. You can't see them apart. If we were just graphing this, let's say, from minus 5 to 5, now the red is the Taylor polynomial because it's going up again. The exponential of the function decays to 0. But in this region around 0, right, we're looking at this Taylor polynomial around x equals 0. Hard to tell them apart. Suppose we wanted to compare them with some other value, like maybe x equals 15. So this is e to the, these are just numbers, e to the 15th, but this is in powers of x minus 15. And let's see what that looks like. If we plot the exponential function as well as this polynomial, well, here's 15. The red has to be the 4th degree polynomial, and the blue, but right around here, you can't tell them apart. Suppose we just do this like in a little interval around 15, maybe from 13 to 17. Okay. So the red is 1, the blue is the other. The blue is the exponential, the red is the 4th degree polynomial. but it looks like they're one on top of each other. You truly can't tell them apart. That's all there is to computing a Taylor polynomial with Maple. It's really fantastically simple. So in the text, this is in chapter 9, section 7. So let's do some problems from section 9.7. Let's do number 17. So in this problem, we're looking at the function sine of x. So f is the function x goes to, well, actually, I don't even need that. I can just write sine of x. We want the Taylor polynomial for the sine of x. This says a Maclaurin series, so that means around x equals 0. And we want the polynomial of degree 5. So we have to look at the first 6 terms. That's what it is. So according to the theory of Taylor polynomials, this 5th degree polynomial should approximate sine x very closely around 0. Let's see. If we plot the sine of x, let's say x goes from minus pi to pi, that's what it looks like. If we plot this 5th degree polynomial, there are only 3 terms. That's what that looks like. Huh. Suppose we plot them together. So I want to plot in curly brackets sine of x, comma, this polynomial of degree 5. So the blue is clearly the sine. The red is this 5th degree polynomial. But in this whole interval around 0, you can't tell them apart. It's such a good approximation. It really is kind of a miracle. Let's look at another example. In the same section, 9.7, suppose we look at the function 2 over x. This is problem 25. And we're asked to calculate the Taylor polynomial for the function 2 over x centered around 1, x equal 1. And we're supposed to find a polynomial of degree 3, so you have to put in 4. And this is this cubic polynomial. And that's supposed to look like 2 over x. It's interesting. Remember, if we plot two over x going from maybe, well, let's see, 0. We're plotting it around x equal 4. So maybe from 1 to 7. That's what 2 over x looks like. It's decaying like that. What does this look like? That's weird. What's going on here? Oh. Centered at 1 of degree 4. So maybe I should graph this from 0 to 3. Yeah, that's what it looks like. And let me graph this from 0 to 3. And how do they compare? Because these aren't drawn to scale. Let me draw this to scale. So scaling constrained. Unconstrained. Let me just plot the two of them together and see what happens. So I'm plotting 2 over x and this polynomial of degree 3. Now that's fantastic. So here, you see the red is 2 over x. The blue is this polynomial of degree 3. And we're approximating the function around 1. And you can see in this interval, the red and the blue functions seem to almost coincide. It's such a good approximation. That's the whole point of the Taylor polynomial. It really is interesting. Let me do one more example in the same section. Problem 29. So we're looking at the function log x, centered at c equal 2. So I want to find, well, actually, let's just look at this. So suppose I plot ln of x going from 0 to 4. That's what it looks like. And then I want to compute the Taylor polynomial of ln of x centered, what does the problem say? Centered at x equal 2. And we want a degree 4 polynomial, so I put in 5. And I get this polynomial of degree 4 plus some error term. Let me plot this polynomial. X going from 0 to 4. So this is the polynomial. This is the log. And what does it look like when I plot them together? That's the interesting question. So I'm plotting together ln of x and this 4th degree polynomial. So this is the Taylor polynomial at x equal 2. And the blue is the logarithm. The red is the polynomial. But around 2, and this interval around 2, they almost coincide completely. Right? That's it. That's how you calculate a Taylor polynomial in Maple. It's just this beautiful, simple command. That's really great. And that